I just wanted to start with also for the crowd with statistics. Basically, how many of you identify like in the quantum doomers party? Like you are more concerned about security than.
I'm a believer in kind of the doom scenario because if we don't recognize it, we can't prepare for it. And when everybody has their head in the sand, then it makes the doom more likely. So I don't think it's absolutely going to happen. I just think that if we don't prepare for it, it will happen. But if we do prepare for it, we can move along, and survive the scenario.
Yeah, I agree with your points. I think we need to be prepared for the worst, and optimism is rare as well. But we need to think about what could be wrong and start to work on that. We have some time. It will not happen tomorrow, but we need to be really careful with our new technology we use from AI to quantum or this kind of new technology, very disruptive technology. So it's all about know what we are talking about and what is coming, and if we are prepared well, nothing can really happen.
Well, this is a new technology. Every technology brings change. That is normal. That's kind of the point of it. We get good things, we get bad things. We know what the road is. We know that we have some primitives that work. We know that we can start swapping the current cryptographic primitives for new ones. So we should just start doing that. There are challenges. This is not something that will be doable within a day, a month, maybe even a year. There are some technical things to do that are new. But this is not a change that will come next year. This is a change that might come in 2 years, might come in 5 years, might come in 7 years. The question is not really, it's not coming next year, it's not coming in 2 years, most likely, so I won't do anything about it. It's about risk and reward. If there is a probability that, 5% that this will come in 2026, you multiply that by the amount of money that will be wiped out if we don't prepare, and that's the cost. So it is a new technology, and personally, I think it is something to be amazed by. It is an incredible technological feat. It brings challenges. We should just, get moving and prepare for it so we can get the best out of it rather than just be scared of what it might change.
Okay. John, can you explain? Sorry, Ian, can you explain? I slept 4 hours yesterday, guys. Sorry. Ian, can you explain in layman terms what is BLS and why it keeps you awake at night?
So BLS is a technique that's used on both the Lightning Network and the Solana network, and in some ways on the Ethereum network. But Lightning and Solana rely on it exclusively. If they don't have it, they're dead. It takes a lot of signatures, combines them into a single fixed size signature to check. If that one signature is valid, then all of the signatures are valid. And it's this great way of just saying, it doesn't matter how big the problem space is, doesn't matter how many signatures there are to check. I'm going to spend the same, 1/10 of a second. And I can check 1 million signatures or 5 million signatures or 10. So it's this great technology for making it very easy to check lots of people at the same time. If any one of them is lying, then the result comes up false, and then you have to recheck them individually or groups of them. So it's this amazing technology for aggregating data, verifying it all in one go, and then knowing that it's correct and no one's submitted false data or had errors in RAM.
And why does it keep you awake at night?
There's nothing like that in post-quantum cryptography. So we do not have anything that has the same performance capabilities. Checking single post-quantum signatures is usually like 3.5 seconds. And normally you have to check all of them individually. There's some really expensive ways of getting a slight reduction in that. So it scales better than, linear. But there isn't anything to transition, Lightning and Solana to. We don't have the mathematical primitives. If we do get them, that's great, but we should still check them for at least 3 years before we actually use them for anything of value, or we're just gambling, essentially. So the reason it keeps me awake is that we're just basically going to have to cross off large sections of high-performant crypto and transition to very slow crypto and some other technique, probably sharding.
Okay, thank you. Lucas, as a entrepreneur working in the Web3 space, what is that you're looking for from quantum hardware producers? Are you like talking with them, or what kind of metrics are you following that I think are relevant for what you do?
Yeah, we are working with them, obviously, to see how far we are from the day it will happen or really happen. We discuss most likely with most intelligent committee in different governments to know how the threat and how it will come and when it will come. They have the best insight in terms of, I think, quantum threat, because they will be the first to be attacked by quantum computing, to have access to really sensitive data and sensitive information. So we know we are not that far of the first attack, but there is a few times between it will become massive, and every organization will be touched. It's not really until a couple of years, but the first government will be really fast.
Thank you. Stefano, can you explain, like, in layman terms, what contextuality is?
Okay, I will have 15 minutes to do this, so I might take all of the additional time that I possibly have. The idea is that there are things that you can do with quantum devices, which don't necessarily mean quantum computers. They can be smaller, simpler. We can manufacture most of them, the small ones today, with current quantum technology. There are things you can do that you can't do classically, that are literally impossible classically. So there's new opportunities. You may or may not have heard of Bell's theorem or non-locality. These are notions in quantum information. The idea is that you can perform certain experiments where you measure two quantum particles and you obtain some outcomes, some bits, 0 and 1 from these particles. And then you look at the distribution. These bits are random. And you ask, could I have foreseen them? Is this something that, could I be fooled by someone into thinking that I'm doing a quantum experiment, but really I have some classical simulator or a small gadget that does it for me? And the answer for well-designed experiments is no. So that's the idea of contextuality. You have some data that you can observe that cannot be reconciled or glued together into a picture where you can predict it fully or even partially. So you get intrinsic randomness, effectively. Randomness that cannot be hacked, randomness that cannot be replicated or predicted. And you can start saying this is a no-go result, which is what it originally was. It was inspired by discussion from Einstein and collaborators early in the past century. And then in the 60s, Bell demonstrated that this was impossible. But really, in more recent years, we got to the point where we realized that, well, I'm saying we, but people much smarter than me realized that this randomness can be used for cryptographic purposes because it is secure in a certain sense. No one can predict it, therefore, no one can really hack it. Once you have it, if you keep it private, it's randomness that's private, and you can use it to make keys, you can use it to share secrets. The challenge really is finding good shapes of randomness for good cryptographic applications. That's the thing that's kind of missing. We know some of them because we've discovered them by hand over the years, but there is quite a lot more waiting, and not a lot of people are working on it yet. Yeah, it's a very promising resource. Contextuality is a resource. It's a cryptographic resource that you don't have classically. You can do new things, genuinely new things.
Thank you. Ian, again, we are probably going into contentious territory right now, but what is, like, I know you've been following, the quantum roadmap by the Ethereum Foundation and what Vitalik commented about it and stuff like that. What are your opinions about that? And probably more importantly, is there some kind of form of engagement from the EEF on the matter that you would like to see?
I would love to see tons of engagement. The plan that Vitalik proposed this year is to wait for the quantum attack to already break Ethereum, and then to rewind Ethereum and all of the layer 2s and all of the bridges and all of the databases and all of the dApps and Bitcoin and any other proof of work system to a previous state in time where the attack hadn't occurred. I don't think that's going to happen. Then he wants to delete everybody's wallets. And that's pretty dangerous. The way that he proposed things to work is that you just get rid of all multi-sig that doesn't come from a wallet. You get rid of basically all custodial wallets, and then you simply use the mnemonic phrase only proven into a ZK Stark because they're based off SHA-256. And we keep SHA-256. And I think that this fundamentally breaks the ecosystem to such an extent that the damage would be a death blow if it was implemented, whether or not it actually saves anything. It's a death blow to the economy, to the trust, to the community. And we need better plans and better communication from the EF to, number one, prepare correctly, because most people don't even have their mnemonic phrases now. And also, we need to come up with a better plan, and that better plan can only be found by consensus in the old-fashioned way, sitting down and talking with each other and with the community and with researchers and experts to really discuss what the different plans look like. So I'm kind of trying to create a nonprofit that does just that for every chain. Just what are our plans? What are the options? How much does it hurt? What is necessary to make that occur? And is there a better path? And do that for every chain, every not consensus mechanism, but for every method of establishing a network communication and a ledger. And there's different opportunities and different challenges for every chain. Like Bitcoin needs opcat. Ethereum had an opportunity for account abstraction, but they let it go. It slipped through their fingers. So now what? We don't know. We just have a plan of rewinding everything and then burning the rest. And I think that Ethereum Foundation needs to be a lot more public about their plans and a lot more asking questions instead of just having a really, really heavy-handed approach. And the Bitcoin community has basically said the same thing, like that heavy-handed approach will not work for Bitcoin. And it may not work for Ethereum either. But I don't think that a heavy-handed approach is the appropriate one. We really need to form consensus. One of my mentors was Paul Monkapetris, head of the IETF for 12 years, and he wrote DNS. He said that if it's worth implementing, it's worth talking about. If you don't talk about it, then you don't know what the shape of the problem is. And was the head of the Internet Engineering Task Force at the time that the internet was created and became popular. I think he's right.
Okay, thank you. Lucas, you mentioned in your talk that Nauris is collaborating with universities all over the world, and that you are producing research and papers. Can you elaborate a bit on how your research looks like internally? What kind of problems you focus on the most?
Yeah, we are focusing on do some research about post-consume and how it will fit with the blockchain technology and the use case of post-consume encryption into real organization, critical infrastructures, banks. We are working with 2 universities in Portugal, 2 PhD and their student on this research. We are working with the MIT in the US as well to see the limit of the post-consume technology and the blockchain generally. We try to we did some papers on a new potential consensus of validation, more efficient and more secure It's really technological research on the use cases as well, and how critical infrastructure will be impacted in the next 10 years about the new technology from AI to edge computing and the decentralized physical infrastructure. It's a big topic these years for us. To how will it decentralize GPU, CPU, and storage, and how we can create seamless technology for to be the most resilient and the most efficient at the same time, which is a big challenge. We all know about the blockchain trilemma in histoire, what we try to solve with this university and scale, create applications that could be scaled for everyone and for the mass. In place of other organization, we help for this mission.
Thank you. Stefano, you told us about what contextuality is. Now the question is it true, and how is it true, if it's true, that contextuality infrastructure needs a different kind of hardware with respect to like universal quantum computers people are working on? Is it more feasible, more hard to produce? What's the state of the art there?
Yeah. So there are two kinds of challenges with quantum computing. One of them is to actually make matter do computations. That is in itself not easy. It is easy for small computations, perhaps. You can always just put a filter on a fiber optic line that does, in a sense, an operation or a gate. Classical optics does that. The hard part is to do it with very large quantum states, so a lot of qubits for a long time. And that's what the challenge of quantum computing today is. Universal quantum computing, I should say, because there are other forms of quantum computing. That's hard. It's hard because of scale. It's hard because of the time that it takes to do the operations and the very short time that these particles live, or well, the very short time that they retain their quantumness, in a sense. Protocols in quantum cryptography and quantum information are very different in that sense. All they need is distance and very limited amounts of computation, typically just a choice of where to measure a particle. That's enough to do a lot of interesting things already. And so you can do them with slight modification on existing classical optics hardware. So if you have fiber optic, if you have a very good fiber optic network, you can probably adapt it to carry quantum states by just using photons. Photons are excellent carriers of quantum state. They live very long. They don't interact with anything else, to the point that we see photons coming from 15 billion years ago in the sky. They just come to us. They've been traveling since the time of last scattering. They're still entangled with the partners that were formed. They've retained their state for all this time. Surely we can do it for a few seconds. The hardware that you need to do the computation is easier. We can do some of it today. It just requires a bit of engineering advancement to make it good fidelity so that you get high key rates. That's the challenge, is to make this compatible or competitive with classical cryptography. We're using keys that are generated in the megabits or gigabits per second. If you do an experiment in quantum on a tabletop, you generate bits per second, perhaps. That's it. So you have to do it right. But it is something that we could do. If we decided that we want to explore that side of computing, it is a lot cheaper than universal quantum computing because we already have a lot of the infrastructure. It's more about finding the applications. That's the hard part.
Thank you. Question for all of you. Do you have any opinions or interesting insights about what is quantum memory? What's the state of it? Why is it useful? Why people should know what it is and stuff like that?
I'll give the bad answer first because the experts are at the end here. So I'll give the bad answer. Quantum memory is like water that's going down a hill, and you need to have the information carried, and then you retrieve it at the right time. The faster the water goes, the more computation you can get out of it, but you need to use more to retrieve it at the right time. It's a really flawed analogy, but the idea is you actually get more utility out of slow memory, but then the rest of your device is also slow. So there's this like performance gain that you can get, but you lose it when you actually use it. There's also there's a bunch of ideas about using silicon for both filtering and for memory. And most of these things are cursed in one way or another. It's really hard to get the information loaded in from the silicon into the quantum system, and then to load that state at the precisely right time. So they have like a whole bunch of extra machinery just associated with, well, maybe we can loop it sort of, but you can't really loop it because you can't do the same thing twice in a quantum system. It would be the end of the universe if we could. Just, it would all go to entropy. I think that's accurate. So it's basically trying to hold information as it's slipping through your fingers, and you have to keep grabbing more and more of it. And the faster you grab, the more you have to grab.
Yeah, I pretty agree with what you said. Internally, we have the debate if we saw the potential of that, but it came with a dilemma with the performance. So currently, we try to be the most efficient and have the most performant system. So overall, it comes with the good and goes with the bad. Currently, I think there is it's surely one of the aspects of the quantum computer. There is the most progress to do it, to improve and find a solution to be more efficient using it. Using other systems that works pretty well. But in 5 years will be another debate, for sure.
Yeah, so perhaps it is worth giving a bit of an overview of why this is hard, because it might not be entirely obvious that it is a very, very hard thing to do. So the idea is you want to keep a quantum state, quantum, not a bit. So it has to be something else. You have many ways of doing this. I mean, you can have a bit of superconducting circuit where the state is encoded on a superconducting current that loops around. You can have a photon. Photons are nice carriers. You can have an atom. It's excited, and its excitation level carries a quantum state. You can have many things. The problems are twofold, really. Depends on which side of the technology you pick. If you pick photons, photons are absolutely great. They keep their state forever. But they travel very, very fast. They have a tendency not to stand still. In fact, you can't make them stand still almost at all. And so the only way to really keep photons confined is to have either something that absorbs and repeats them, but that process is even slightly flawed. Even like a 1 in a million imperfection, the photon travels a lot between the two endpoints of your receiver. It will bounce billions of times before you can use it, maybe more. So you will almost certainly lose its state in this way. The other way is to make a very big loop of fiber optic, or a chip that has a very long path on it. And that works better, in a sense, but is also a bit lossy. Every time it reflects against the side of the fiber optic or against the side of the chip path, you have a very, very small probability, because of imperfections, that the photon will be lost. And so, because photons travel really fast and bounce really fast, that accumulates really quickly over time, and you don't have a long life. For the other kind of technologies, it's mostly that the world is hot, like very hot. And by hot, I mean it's hotter than absolute zero, which would be perfect. And so for some of these technologies, you have to cool things down to 10,000ths of a degree above absolute zero, in part because you want superconducting effects, which happen there, but in part because every time you have heat is a soup of photons. These photons have a chance of interacting with your quantum states. If they are of the correct energy, they have a very high chance of interacting, and they carry away the information. One bounce from one photon from the heat bath around your computer is enough to screw one qubit. And so you have to lower the probability that this happens, which means you have to cool things quite a lot, quite literally. And so it's hard to find a technology that is both something that you could use at actual room temperature or that you could carry around in your pocket in a ledger, and at the same time keeps a quantum state for any longer than a few microseconds. These days, we're actually up to seconds, I think.
Which is incredible.
Which is incredible. Like 2 years ago, it was micro, now it's seconds. So it's improving. But I think as long as you don't have universal quantum computing, this is going to be a challenge. With universal quantum computing, you can do what Ian described earlier. You can just continue to correct. It's going to try to slip, you catch it, and you put it back. And you try to fix the errors again and again and again. But that requires a very big machine. So it's not something that we can do right now. I mean, maybe in a year or two, but only for very few qubits, and definitely not in your pocket. So there are some advancements that need to be made here. If we don't want to have the quantum internet that distributes these particles on the fly, which by the way is an option, we need to do better on quantum memory. But people are working on it quite hard.
So it gives the wrong vibes. Heat gives the wrong vibes.
Heat gives literally the
As
wrong
in
vibes.
vibey modes
Yes.
of, yeah.
Yes. Literally the wrong vibes.
Okay, cool. I would say maybe last question, which is not really a question. So this is like super early, right? Like the interaction between quantum and Web3 tech. I don't say quantum and crypto because this is one of those contexts where crypto is really in a superposition of the word cryptography and the word cryptocurrency. So that is possibly the worst pick at the moment. When I say quantum crypto, it's like doesn't make anything clear. So it's super early for quantum and Web3 tech interaction. It's a super early space, and I think very few people know about this right now. Obviously, many people that build a knowledge in quantum computing maybe lack knowledge in Web3 technology. And many people that built knowledge in Web3, like I guess many of the attendees of an event like this, probably have never really approached quantum computing. Maybe they read something, but I wouldn't expect that there are many cross-domain experts. So if you were to like go back, what kind of path would you suggest is the best one for people to build information and start, knowing more about this world? Like literally, okay, I played in Ethereum for like a couple of years. Now these things come up. What do I do?
Okay. No, that's a very good question. The thing with blockchain is way more easy to learn about blockchain than quantum computer or quantum physics. But everything related to quantum in overall is kind of private for now. It's hard. You need to be in some very specific universities or very big group, big enterprise to have the chance to work on quantum. So blockchain was easier for everyone to learn about that, about what's even the technical part of blockchain, about encryption, smart contracts, and that's true as well. In the other side, from quantum, they didn't really learn about how blockchain works, encryption model using blockchain, and how everything could be compatible to boost even the research, boost the data management overall, boost the hardware requirement. And I think both could be really compatible. If you are a blockchain enthusiast, start looking about quantum and what will happen in the next 5 years, because we saw recently the disruption of AI, but quantum will be even bigger. Because the research in terms of pharmaceutical or medical or technology will be way faster. And I think quantum in the mid-long term will be combined with AI and create a real AGI what we should be afraid of that. By the way, that's not really the talk of today, but quantum AI in blockchain should match in the future. We should see more quantum application, bridging blockchain perspective and AI model into connected to that to boost even the research on quantum hardware. There is a couple of things to do right now, but overall the two are really compatible, I think, and there is a lot of common application. Even if there is not a big focus from the Web3 community right now on that, but it will come in the next couple of months for sure.
So I'd like to agree with what you said, but add quite a bit. So I define Web3 as JavaScript on a web page that goes to blockchain or some other kind of distributed ledger. And there's been a lot of like redefinitions and like people trying to do marketing around what is Web3, what is Web5, what is this, what is that. And this is just part of their marketing gimmick. And knowledge is a way to cut through the bullshit. If you actually understand how these things work, you'll be able to separate the bullshit from the reality in any topic. And so you just become more capable and well-armed and able to figure out if someone's just trying to scam money out of you. The more you know, the better off you are. I do think that there is a lot of resources for quantum, and there's a lot more for blockchain, but a lot of the blockchain resources are focused on the fluff. You don't need to study consensus models as long as you're using technology that has not too much innovation. If there's a lot of innovation in the consensus model, you're adding the possibility of double spend. Yes, you can spend many weeks studying consensus models. I've spent months doing it, but it has very little utility. As long as they're not doing something crazy, you don't need to know too much more about it. The thing that really makes a lot of sense to study is JavaScript on a web page, reporting to a smart contract. Learn a little bit about how the storage works, because the storage is going to be different for each chain. Cosmos has a different storage mechanism. Solana has a different storage mechanism. Ethereum, has kind of like a shining storage mechanism that was pretty well designed. But if you look at the problems that is created from the storage mechanisms, you'll see that there's people trying to solve those problems. So the sky's the limit on storage mechanisms, but it's useless to study lots of consensus models. For the interaction between quantum, I would suggest starting off at like the IBM guides. You can start learning about quantum algorithms. You can program in Python to perform the quantum computations. There's a bunch of new computing centers that are, IonQ, I think, has one. There's a bunch of places you can just run their quantum computer. And they're all pretty much compatible with Qiskit. There's a few exceptions, but Qiskit's the main way to get started, and it's Python. You can do D-Wave programming with Qiskit, but D-Wave is limited. I think that there's a future for Web3 and quantum to coexist. When we have these quantum key distribution networks, like the one from South Korea's SK Telecom, the bank networks that are growing, there's new networks that are being created. Those still need to communicate with the Silicon world in a trustless manner, and blockchain is a really good bridge between those two systems. So I think the blockchain, Web3, and quantum will actually pair together very well in the next 1 to 3 years, and there'll be more and more projects that are pairing them together in different ways. So it makes sense to actually learn the depths of both, but also to figure out, when someone's just trying to shine you on and trick you. In the case of quantum, there's a lot to learn that's very strange, very, very bizarre. The stuff I studied in physics in the 90s is just useless. I had to start over. And it is going to be months of study if you want to learn the physics. And in my case, I hired a quantum physicist who specializes in algorithms as an advisor, and I ask him questions on a regular basis to check my understanding. And it's the that's not going to be a very common resource that people will have. But it's one of those things where when I'm on stage, I feel like I have to get it right. And if it's just your own understanding that you're risking, then it's fine. But if you're the more money you're talking about investing into something that's post-quantum, the more you should ask people, is this post-quantum? So I'm hoping to make that resource more available, just having a forum or community that just focuses on quantum versus Web3, what is the migration paths? But I've been just, ripping apart white papers, and sometimes I'll say, this is really good tech, but that's rare. So there's a lot to study, and it's worth doing.
Stefano?
Yeah. So, yeah, that's a hard question. There are two sides of things. One is the post-quantum cryptography side of things, where you really have to know what people can do in quantum, and the rest is really cryptography. It's classical cryptography. It's just cryptography that you have to know is robust in some way. If you're studying weaknesses, you have to know what the state of the art is. That is one challenge in itself. That requires you to read a certain kind of papers from a certain community. You have to keep up with hardware manufacturers and have a good idea of what's feasible and what's not feasible. That is hard for people in quantum. I imagine it's hard for people outside of quantum as well. But more generally, we have a UX problem in quantum. We have a huge problem. It's the way that quantum is presented is hard to approach. It has been for many years. It has been for 100 years, actually. It requires a certain mathematical background. It requires a certain training. Luckily, things have changed. There are more modern languages. There are more modern ways of approaching quantum. And you can learn enough to do sort of quantum-enabled cryptography, contextuality, non-locality, actually, I would say within a few days or maybe a week or two. I certainly hope that my students pass their exams this time, and we will see. No, I know that they do well typically. So there are more modern methods that you can use for this, but we do have a problem. We do have to make things more accessible. We do have to build some tooling. We have to offload some of the hard stuff to a computer. Otherwise, it's like asking people to compute logarithms in their head. Why would you have to do that? You have a calculator. Same thing here. Why do you have to do contextuality computations in your head or by hand? You don't have to. There's standard mechanisms. We can just build software to do that. I think that's the start to make this more mainstream. We need it to be approachable. We need the parts that are confusing because they happen in 1,000 dimensions with millions of vertices. We need those, that's what a computer is good for, not our brains. So we need to conceptualize it better. We need to encapsulate it better. But I think we have plans for that.
Yeah, we do. Okay, thank you very much. I hope this was insightful. And yeah, I think that's it.